Okay, great. So I'm Dane Danielson. I'll be speaking about some joint work with Gautam Sadishchandran and Bob Wald. I'm at the University of Chicago right now. So to begin, I'm going to start with something that may be familiar but might need to be refreshed, just to introduce this concept of charge superselection. So famously, if you integrate a Gaussian surface at infinity, you get the total electric charge. I'll be talking about E and M to begin with. And that total electric charge commutes with any local gauge invariant operator O. And that implies that the matrix elements, the off-diagonal matrix elements of O, are 0 between eigenstates with different total electric charge. So that has some implications. It says quantum interference is forbidden between states of distinct total electric charge, or put differently, superpositions of differently charged states are totally decohered. What's maybe less familiar is that in asymptotically flat spacetimes, as in scattering theory contexts, there are infinitely many more asymptotic charges that exist, one for every function on the sphere that you can integrate at infinity. All of them are conserved, and rather than total electric charge, the higher angular moments of these charges decohere electron or charged particle momenta. So put differently, electron momentum eigenstates are also eigenstates of these higher harmonic asymptotic charges. And just like before, any local gauge invariant operator commutes and with this thing, and also has 0 off-diagonal matrix element. But now you have 0 off-diagonal matrix element with respect to electron momenta. That's a disaster because wave packets are famously coherent superpositions of, say, electron momenta. So if the theorem that we've proved is that on gauge invariant observables, the ordinary undressed electrons and positrons of scattering theory are, in fact, space-time translation invariant states in the bulk of an asymptotically flat spacetime. So I send in my nice wave packet, and I end up with splat, this junk space-time translation invariant state in the bulk. It looks nothing like a wave packet. It looks nothing like an electron or a positron that we know and love in nature. So then this begs the question, what are the physical states of QED, if not these things, in scattering theory? Well, we can answer the question by considering a thought experiment. So suppose our hero Alice releases an electron from a screening potential in the bulk of the spacetime. The effect of the screening potential is to set the higher harmonic charges into a 0 eigenstate. And when this electron arrives at future time like infinity, it started out as some localized wave packet, and it will arrive at time like infinity in some superposition of momenta coming in. But as we learned, those momenta carry different higher harmonic charges, and higher harmonic charges conserved. So how do we square this with the conservation law for these charges? Well, photons can also carry higher harmonic asymptotic charge. So the conservation law demands that soft radiation must be emitted to compensate and maintain the fact that this is a 0 higher harmonic charge eigenstate. So to produce a bulk electron in scattering theory, we can just reverse this process. We can just take this data at future null infinity and future time-like infinity, time reverse it, and send it in. That requires maximal entanglement between the electron momenta at time-like infinity and the photon momenta at scry. And we show that the only states that aren't subject to the disastrous decoherence we just described before are precisely these states. So these are the physical states of scattering theory in QED. Okay, so let's think of, now that we've got a feel for this soft photon stuff, does it have any observable consequences? You know, famously, people will say things like, if it's larger than my detector, it can't have any observable consequences. But that, in fact, is not true. Because if you're entangled with something larger than your detector, even if you don't observe it, it can decohere you, and that can have observable consequences. For instance, the soft photons that are radiated when you release the electron from a trap give rise to an enhanced rate of wave packet spreading. Logarithmically in T, this is a correction to the standard wave packet spreading in Schrodinger quantum mechanics, but it's a very small effect. I wouldn't go out and look for it anytime soon. Moving to quantum gravity, the same thing happens in linearized quantum gravity, and it's an even smaller effect, but again, logarithmically growing in time. And there are some other consequences. If Alice uses a Stern-Gerlach apparatus to make a spatial superposition of a charged particle, and then allows the branches of the wave function to coast for some time at different momenta, then brings them back together, will it be coherent? Well, if you've been following along, the fact they're on different momenta implies that no, there is a limit to how long they can coast at different momenta, picking up these different higher harmonic charges before they're inevitably decohered by soft radiation. And this gives a maximum size for a spatial superposition in QED, and again, in linearized quantum gravity due to the analogous effect with soft gravitons. And again, it's a big superposition, so I wouldn't hope to measure it anytime soon. Okay, so finally, you know, we've mentioned briefly a little bit about quantum gravity in the context of linearized quantum gravity. But you know, if you start to take nonlinear effects into account, you really talk about the full nonlinear quantization of GR, which can be done on the boundary of an asymptotically flat spacetime. Don't ask me about what UV completion in the bulk. Well, the same story goes through. Again, you have these charges, but unlike in QED, there is no analog to the dressing procedure that I constructed by releasing the particle from a box, because gravity can't be screened. And what this means is that all all states on the local gauge invariant algebra of quantum gravitational scattering, all those states are space-time translation invariant. That sounds like an utter disaster, and there's no way to fix it up because there's no dressing, but famously, there are no local gauge invariant observables in quantum gravity because this word local is in contradiction with this word gauge invariant. So what this suggests is that, in fact, the resolution in quantum gravity is quite different, that all bulk states on the gauge invariant algebra pertain instead to relational observables, as one might expect, although this is a different way of seeing it, or put differently, kind of non-local objects or extended objects in space-time. Right. So that's all I have to say. And well, it's brief, but this is work to appear soon. And also, well, I'll be on the postdoc market this year, so I'd be happy to chat more about it in that context. So thanks.
Let's thank our speaker. Any questions? Oh, okay. Question? No. Okay. Maybe I had one question. So, undressed electron, can you explain that a little bit?
Oh, yeah. So an undressed electron is just any electron that you would have thought is ordinary good scattering data if you read Peskin and Schroeder or Weinberg. You know, well, yeah. So, but if you're very careful and you send in this maximally entangled state, it's incredibly fine-tuned state, where every momentum mode of the electron is entangled with an formally infinite number of soft photons that are tuned just for that momentum mode. You do this procedure, you get a sensible bulk electron. But if you just send in an electron wave packet, it behaves like nonsense. Of course, you can still, it behaves like nonsense in the sense of plane waves. It behaves like a plane wave. And if all you care about is kind of central momentum scattering type questions, you can still get the right answer.
Okay, thank you. Let's thank our speaker again. Oh, you have a question? Okay. You have like 10 seconds.
I think this is a quick one. In your last slide, when you talk about observables being, wave packets, wave functions being translation invariant
Yes.
in an asymptotically flat space-time, what does translation invariant mean when you don't have a flat space-time?
Yes. So what I mean is that the generators of space-time translations, at infinity, act in a, you can prove that whatever it is they do in the bulk, you're invariant under that. Yeah.
Thank you. Let's thank our speaker again.